Okay, let's start this next session. So I've met a lot of you. I'm Daniel. I'm in Travis Wheeler's lab, and my work these days is mostly in deep learning focused around genomic sequence and protein sequences. And I was super excited to have the opportunity to talk to you all about machine learning because this is like the coolest field right now. This is, this has all the force of physics in the 1900s and all the force of mathematics in the 10th century. This is like everything. And I was going to do a brief history on deep learning and biology, but, I don't think it's that interesting. The interesting part of all this history is like a bunch of failed results and then AlphaFold, which is just like amazing. And so this is AlphaFold 2. And to preface this, when I started my PhD, people said that this was an impossible problem. People that worked on predicting protein structure were sort of laughed at because it was just too hard. There was no way to solve it. And now, if you talk to a structural biologist, they'll say this is a solved problem. Nobody is working on this problem anymore. It's over. So to demonstrate that, we have an experimental result compared against AlphaFold's result. The experimental X-ray structure of this protein is in green, and AlphaFold's prediction is in blue. And you can see AlphaFold does a pretty incredible job. And the whole reason AlphaFold is doing this is because of this big boom in deep learning. And so I'm probably one of, yes? It depends on how disordered the protein is. And so the question was, how does AlphaFold do on sort of disordered proteins and protein regions? And the answer is, it sort of depends on the protein and how large the region is. So you can see there's some not super well organized sections of these proteins, and AlphaFold does an okay job. For really large globular proteins, AlphaFold does do a little bit worse. But at the same time, you don't have super great crystal structures for those proteins usually either. Yes?
So the name disordered is for a reason, because it is disordered in the natural environment. So it is not a fair expectation to have a disordered region to have an ordered structure. What typically a disordered region does is like, it changes its structure depending on the surrounding environment. And it is not, we should not expect any program to give a structure to a disordered region, because then it will be falsely claiming it's an ordered one. So you have to live with it, and you have to be smart how to deal with it.
Thank you for that. So I think I'm one of like 5 people or so here that is interested in deep learning just for deep learning. And the rest of you are interested in really cool biology stuff. But the thing is, there's an intersection here. All of your careers, all of your research careers is going to be very affected by deep learning. And I think that this is a great opportunity to sort of get an intuition behind what's possible, what some of the limitations are, and what some of the strengths are. So let's see. So this is sort of the plan of what we're going to do. We are going to think a little bit about neurons and neural networks, which is synonymous with deep learning, and we're going to think about what they actually do. And then we're going to have a small activity where we play around with the weights in individual neurons and try to solve some puzzles. We're going to go on from there and talk about more full-scale neural networks and think about how they learn. And then we are going to do a couple activities, one of which is going to be recognizing handwritten digits using a neural network. And another one is going to be actually doing the model that we were using in the last session. So we are going to be predicting binding affinity, which is pretty cool. And finally, we're going to finish up with convolutional neural networks and with a activity where we are going to predict secondary structure using convolutional neural networks. And we're starting a little bit late, so I don't know if we're going to get through all of this. We'll get through as much as we can, and I can send you guys the materials for whatever is left over. We have a huge range of experience in the room, so if this ends up going slow, that's absolutely fantastic, and we'll just work with what we got. Okay, so deep learning is sort of a nebulous term right now, and the traditional definition isn't quite what people use for deep learning anymore. But the traditional definition is good enough, and the traditional definition is pretty much neural networks. So you can think of any sort of deep learning method as being a method that uses neural networks. And the idea of neural networks is pretty straightforward. So in the 1950s, and before actually, but in the 1950s especially, people were thinking about how people think. So, you have a person, and they look at a beautifully drawn flower. And one question that we might ask ourselves is, how is it that this person is able to look at this flower and recognize that this is a flower? And so what people sort of imagined, and experimental data helped them imagine this, but what people sort of imagined is inside this person's head, they are having some neurons that are grabbing the raw sense data of this flower. So, instead of viewing the flower as a whole, they'll view small chunks of the flower, and that's going to be represented as neuron activations in their head. And then we're going to have downstream neurons, which connect to all of these sensory neurons and ask simple questions. And so maybe one of these neurons is asking, is there a lot of green in what I'm seeing? And there's a lot of green, so this is going to positively activate. The next neuron might ask, is there any sort of sharp objects in what I'm looking at? And there aren't really any sharp objects, so this one's going to negatively activate. And maybe this one asks, is there a lot of sort of bright, vibrant colors? And then there's some, purple and green, so there's a little bit. And then, maybe the last one asks, is this a connected object that I'm looking at? And it is a connected object. So each one of these neurons is asking a little question, and it is activating positively for one answer, and it is activating negatively for another answer. And you can imagine we can have another layer of neurons that's asking another set of questions, and we can have another layer of neurons that's asking more questions, and so on and so forth. And eventually you have one neuron, which is the flower neuron. And it probes this last layer of neurons, and it tries to figure out, is this a flower? And if things are working right, it will correctly identify that as a flower. So the question that sort of comes up with this conception of a neural network is, what is a neuron actually doing? What is the actual computational unit that we're dealing with, and what sort of questions can it ask and answer? And the answer is, a neuron is a real dumb thing. So here's going to be our model neuron, just labeling some parts. The neuron that we are caring about is this Y1, and it is connected to the previous layer, the inputs, which is going to be X1, X2, and X3. So in addition to these neurons, we have three other things that we're going to parameterize, and that is the weights. So each one of these connections has an associated weight, W1, W2, W3, and the only computation that this neuron, well, actually, hold on just a second. And so in our brain, our neurons are these electrochemical machines for activating. Well, every single activation is represented by some electrochemical reaction. But given that we're working with computers, we have to have our activations represented as numbers. And so for this demonstration, I'm going to have positive activations be in the range of 0 to 1, and negative activations be in the range of 0 to -1. Okay, so moving on. The only computation that a neuron can perform is a simple weighted sum. This is what a neuron can do. It can't do anything more complicated. All it can do is it can multiply the activations of the previous neurons by the associated weight. So for our Y1, it is equal to W1 times X1 plus W2 times X2 plus W3 times X3. And you might say, well, that seems like a real dumb computation. What can you possibly learn? And it is a really dumb computation, but it turns out you can learn a whole lot. So one simple question that we could ask is the sum of all these things positive? Is the sum of all of our previous neurons a positive activation? And you can imagine to answer that question, we just need to have our weight set to 1. And when we do that, we just have a direct sum of all of our activations. And if that sum is positive, it's going to be positive. If that sum is negative, it's going to be negative. So we already sort of can answer some interesting questions about the previous activations. And as another example, here is a whole bunch of positive activations. And the problem with this example is if we add all of these up, we get a number that's bigger than the range of activations I was telling you about. I said we want our activations to be in the range of -1 to 1, but we have so many positive activations in the previous layer that we have this sum up to 2.4 outside of our range. So we're going to introduce one more component to our neuron, and that is the activation function. And the activation function is a nonlinear function that's going to usually squash our output. So in this case, the activation function that we're going to be using is the tan-H function, and there's a million different activation functions. Tan-H is nice, though, because it is going to squish our output to the range of -1 to 1. So in this graph, you could sort of make out, it's a little bit blurry, but if you have an activation that is -infinity, that's going to become -1 after TNH. And if you have an activation that is positive infinity, that's going to become +1 after TNH. And so it's squishing our output to be in that range that we want of -1 to 1. Okay, so we pass this calculation through our activation function, our TNH function, and what we end up getting is 0.98, which is in our range of 1 to -1, which is nice. Okay, so although we have this activation function that's kind of nice, it's still real dumb. You know, the neuron cannot answer very many interesting questions. And in the current form, it actually can't answer as many questions as we want it to. So here's an example of a question that this neuron is going to have a hard time with. I want this neuron to compute a weighted sum, or excuse me, a mean. I want it to take the mean of x1, x2, and x3, and if that mean is greater than 0.3, I want it to positively activate. And if it's less than 0.3, I want it to negatively activate. So let's see, in this example, everything adds up to exactly 0.3, and we're going to call that a borderline positive activation. And this example, things add up to 0.1, so that's a mean of 0.0333, which is less than 0.3, so this should negatively activate. Okay, so we can take the mean of all of this pretty easily. The way that we're going to do that is we're just going to set each one of our weights to 1/3. 1/3 of x1 plus x2 plus x3, that is going to be the mean of x1, x2, and x3. But to be able to actually figure out if this is greater or less than 0.3, we need one last part for our neuron. And that last part, that last part is going to be what we call a bias term. And so this is just one extra thing that we're adding into the sum. It is a weight without an input. It just gets added in. And we're going to set that weight to be -0.3. And now the only time this sum can get larger than 0 is if it's greater, if the mean of x1, x2, and x3 are greater than 0.3. If the mean of x1, x2, and x3 is not greater than 0.3, then the bias term of -0.3 is going to outweigh that, and we'll get a negative activation. And in this case, we get a negative activation, even though the value without the bias would be positive. So it seems like it's working here. So that is a neuron. That is all we can work with when we are dealing with neural networks, is a whole bunch of neurons. And the fundamental calculation that they're doing is this on the screen. You know, we have our activation function wrapped around a sum of all of our weights times all of our inputs plus the bias term. And an important thing to note here is the only thing the neuron is allowed to change, the only knobs we can twist on our neuron to tune its calculation are the weights and the bias. We don't change the activation function. We don't change the inputs. We can only change the weights and the bias. So that's what a neuron is, and we're going to do a little collab thing right now. So I'm going to put a link in the Slack channel, and hopefully it works for everybody and we can start on this project. Also, while I'm doing this, are there any questions? Sorry, what's that? Exactly. Hopefully everybody understands what a neuron is. And I bet there's a lot of people in this room that had a much better understanding of what a neuron is before this. But okay. So I'm sending a collab page on the Slack channel. So if you go to the lecture materials and you click this link, you will get a page like this. You'll need to sign into your Google account. And I'll wait just a couple minutes so people can get all set up. Everybody has one? Does everybody have a Google account? Or a better question, does anybody not have a Google account? Okay. And once you have this up and running, can you put your hand in there? Okay, awesome. Okay, so Google Colab is basically a Jupyter notebook in the cloud. And what that means is it has the ability to have, bits of text and also bits of code. And the code is kind of nice because you click this button and you will get a notification that I made this, you didn't make this, and Google didn't make this. Will run anyways. And what's going to happen is Google's going to spin up an instance of a VM on one of their machines, and they are going to run the code inside this cell. All of this code is Python. If you aren't super familiar with Python, that is completely okay. There shouldn't be a need for any super expertise in Python today. But so what we're going to do is we are going to run each cell in the setup section, which is all of this. And that's going to allow us to run the code and the puzzles a little bit later. Okay, has everybody ran the cells in the setup section? There are 2 cells, that is correct. Okay. So if we go to the simple neural network section, I've made a little helper class to make it easy to create and visualize neural networks. So here is one line of code to create a small neural network. This one will have 2 inputs, and it will have a hidden layer with 3 neurons, and then it will have 1 output neuron. And if we press play on the cell, we'll draw the neural network, and we can see what's happening. Okay, so task 1, super simple. What I want you to do is I want you to replace the question marks, and you can look up here for inspiration, but I want you to replace these question marks so that we have a neural network with 4 input neurons, and then a hidden layer of 3 neurons, and then a hidden layer of 2 neurons, and then 1 output neuron. And if anybody is having any trouble at any point during this, feel free to raise your hand. Right, so move all the question marks and then put in numbers, something like this to try to make a neural network with 4 inputs, then a layer of 3, and then a layer of 2, and then 3, 2, 1. And let's get rid of these question marks. That'll be fine. Okay, let's try pressing. Let's scroll down just a little bit. Okay, so go all the way up. Scroll all the way up. And down just a little bit. Press the play button. Okay, and if anybody is having an error while trying to run one of these cells, make sure that you press the play button on the first 2 cells in the setup section. Okay, now let's try that again. Perfect. Okay. Okay, how are we doing? Okay, I'm going to put in the solution here. Okay. Okay, forward and onwards. So one thing about these neural networks, and really any neural networks, is that they are initialized with random weights. Oh, yes. Oh. Okay. Thank you. Okay. So one thing about these neural networks and any neural network that you work with pretty much is the weights are randomly initialized. And so what that means is that if we have a fixed input and we pass it to 2 randomly initialized neural networks, we're going to get different results. And so this cell sort of demonstrates that. We create an input of 1s, and then we're going to pass that to different versions of the same neural network. So the structure of the neural network isn't changing, but the weights on each iteration of this loop is going to change. So if we press the play button here, we'll see even though the input does not change at all in this loop, we still get a different output each time. And we can visualize this also with a slight change in this. So let's see. With this draw equals true, we can visualize the activations throughout our neural network. And so once again, even though the inputs for this neural network doesn't change, we can see that the activations do change. And the reason the activations change is because the weights are changing with each iteration. Okay. So let's see. The way that we can mess with the weights, at least for this, this class of neural network, is like this. And this code is sort of ugly, so whenever you need to mess with the weights in this notebook, I will have all the weight editing stuff there, and you'll just have to put in numbers. But the important part is that we can change the weights, and if we change all the weights and all the biases to 0, we'll get a complete 0 activation. If we change all the weights to 0 and the bias to plus infinity, we'll get a positive activation. And if we change all the weights to 0 and the bias to negative infinity, we'll get a negative activation. So doing that, we'll get these results. And so this first picture is random initialization. So these are random weights. The second one is 0 weights. We have a 0 activation here. The next one is a negative bias. And the final one is a positive bias. Okay. So here comes the fun part. We're going to do a couple of different puzzles. And I've finished one of these puzzles so that you can sort of look at it and get a sense of how you're going to try to complete this. So the first puzzle was to figure out if input 0 and input 1 is greater than input 1 and input 2. And so to do this, I made a neural network that takes in 4 inputs and it has one single output. And I've made the weights of our 0th weight, so the weight that corresponds to input 0, 1.0, the weight that corresponds to input 1, 1.0, and the weights that correspond to inputs 2 and 3, negative 1.0. So I've sort of put them at opposite ends of the balance, and then this has no bias. And when I run this cell, because this is a valid solution, we draw the network, and because the solution is valid, we'll get this success message. So for the next couple minutes, what we're going to be doing is completing the rest of these puzzles. At the top is going to be a comment that explains what your goal is. And over here is going to be question marks where you should put in values for the weights. And that is it. I'll be walking around. If there are any questions, feel free to raise your hand and I'll come over and help. So go to the top. Okay, we need to press the play button on this one. And so if you don't press the play button, then the code doesn't run. Press the play button and it runs. Then we can use all the tools. Perfect. Feel free to go on to the next one. Blank report. Okay. So if we look at this, for example, so this is our first input, our 0th input. So what we figure out what weight find that work so that we puzzle. We want to make it so 2 inputs. If they are both +1, then we want a positive output. And if either of them is negative, then we want to make the calculation. And so we want to figure out the weight so that that happens. Oh, okay. So what's happening is this neuron's value weight plus this weight times. Exactly. So for this one, okay. Either of them. Okay. Let's walk through the solution for the or puzzle. Or is that the first one? No, the and puzzle. Okay. So the problem here is we're trying to compute this logical and. So we have two inputs, and if both of them are +1, we want to output a positive value. And if either of the values are -1, then we want to output a negative value. So let's see. What I'm going to do is I am going to assign both of these a positive weight of 1.0 And it doesn't have to be 1.0, but they should both be the same value. And I'm going to assign our bias a negative value. I'm going to say negative 1.2. And so the thinking here is that if only one of these is positive, then the sum here is going to be 0, and our bias is going to outweigh. If both of them are positive, then the value is going to be 2, and our bias is going to subtract that, make it 0.8, and we will be positive. And following the logic here, if you haven't thought about circuits and you haven't played around with this sort of thing, it can be a little bit tricky. It's just sort of figuring out how we can get the logic to correspond to the weights. And it just, it takes a little bit of playing through. So this is what I'm going to try. It might work. I can imagine it might not. Okay, it works. Okay. So once again, what I did is I just added our inputs, and I said they have to be larger. The sum of these two inputs has to be larger than 1.2. And the reason they have to be larger than 1.2 is because if they are both positive 1, then they should be 2. The sum of x1 and x2 should be 2 if they are both positive 1. And in any other case, they should be 0 or negative 2. And in both of those cases, this randomly picked bias of negative 1.2 pushes us over this threshold and makes it so that the only time this will positively activate is if both of our inputs are positive 1. Okay. And if you are having a hard time following this part, that is completely okay. The rest of the activities, we are not handpicking weights. We're going to spend just a little bit more time on the remaining 2 puzzles, and then I'll show the solutions for those. Just kidding. Ron is doing. So that's that. And so it's in there, but I freaking backwards.
So it's just like
And just a quick show of hands. How many people have made it through the and puzzle? Okay. How about the or puzzle? Excellent. What about XOR? Okay. We'll spend just a couple more minutes here then. Okay, I think we're about ready to show solutions and move on. And so this is a really tricky thing because first off, you know, hand picking weights is hard, and also logical circuits are hard. So we're combining two things that a lot of us just don't think about regularly. And that makes it tricky. But so here are some solutions. So let's see, this is the logical OR. And if either x1 or x2, if either our first input or our second input is +1, then we want this to be positive. So what I'm going to do is I'm going to use weights of 1. So this is just the sum of our inputs. And then for our bias term, I'm going to use 0.1. Okay? So let's imagine what could happen. If they are both +1, both of our inputs are +1, then they sum to 2, and that, of course, is going to be a positive activation. If exactly one of our inputs is +1 and the other is -1, those will sum to 0, but we have this bias of 0.1, so it will pass the test. If they are both 0, though, or excuse me, both -1, then they will add up to -2, and even with our positive bias of 0.1, that isn't going to affect our activation. We'll have a negative activation. So if we run this test, okay, perfect. So this one is the trickiest one. So this puzzle is the exclusive OR function. And the way the exclusive OR function works is that we get a positive output if and only if exactly one of our inputs is positive. And so if we have the inputs +1, -1, that's positive. If we have the inputs -1, +1, that's positive. But if we have the inputs -1, -1, or if we have the inputs +1, +1, the output should be negative. And so exclusively 1 can be positive. Okay. And let's see, I don't have these written down, and this is a pain to do. So let's see if we can do this. Actually, you want to come up here and put in your solution?
Uh, what is the term for reverse?
Or-
Supplement?
Sure.
Yeah. So basically what we are doing is we are going to the weight set to basically I just copied the formula of the Boolean algebra. So the first term would be the weight would be negative because one is one input would be A, then the next would be B would be the supplement. So -1, and then the bias should be this is a AND gate, so -1. Perfect. And this would be also a AND circuit, but it will be the reverse of the previous one because this time A gets the negative A, supplement of A, and B gets normal B. And this is also a AND formula. After getting these two, we have the same weight would be the same, and the bias would be 1. So this should work actually.
Okay. What happened?
Yeah.
Success.
Yeah, I'm not good.
No, that was fantastic. Okay, so let's think about what's happening here. What the solution was is to realize, you know, having just one, yes. Oh, excuse me. Well, actually, I want this picture for right now. So what we realized here is that just having one circuit wasn't enough. And so, you know, in all of our previous examples, we have one circuit and we can just compute that circuit with a single neuron. What we've effectively done here is we've made our final neuron the combination of two other circuits. And so we sort of have this 3-circuit solution, including this neuron. And what this first circuit does is it is saying, well, if you are both positive, so let's see, if our first value is positive and our second value is positive, so imagine x1 is, or x0 is positive and x1 is positive, we will have +1 plus -1, that's 0, plus -1 for our bias. So we will have a negative activation. We have that negative activation if they are both 1. We also have something on the other end. So this is a negative activation if our first input is negative and our second input is negative. So we're doing the reverse here. So the first time we're checking to see if they're both positive, and if they are both positive, we are outputting a -1, and if not, we are outputting a +1. And in our second circuit, our second neuron, we are computing the opposite. So we're computing if they are both -1, in which case we output a -1, and otherwise we output a +1. And finally, we do an OR. We say if an input passes these tests, then that's good enough. And so if we have exactly 1 or both of these tests being passed, if we have a +1 coming out of both of these circuits, then we are going to say it passes the test and we are going to have a positive value. And this is a really tricky one because exclusive OR is a bit of a pain to implement, even if you are just doing the circuit diagrams of it. And when you're doing it in a neuron, it becomes much more tricky because editing a bunch of weights is hard. So that is the solution. If you didn't arrive at all these solutions, or you still feel a little bit fuzzy about how these solutions work, that is completely okay. The point of all of this wasn't that we become experts at Boolean logic, although that's a great outcome also. The point of this is just to show, neurons are capable of more than they seem, and they can do sort of interesting logical things. Okay, so let's continue on. Okay, so we're going to continue on, and we're going to think about more we're going to step back a little bit. We aren't going to think about the individual neurons. We have this idea neurons do this weighted sum to compute things, and you can combine multiple neurons in different layers to do more advanced computations. And in the last set of problems, we were sort of dealing with 2 different types of neural networks. One looked like this, where we had one layer of inputs connected directly to a layer of outputs. Another sort of neuron or a neural network looked like this, where we had our inputs connected to a hidden layer connected to an output. And in the last problem, I stated that the exclusive OR could not be solved with the first neural network. It could not be solved with the neural network on the left. And so one question we might have is, well, what sort of problems can you solve with the neural network on the left, and what sort of problems can you solve with the neural network on the right? And the answer is the neural network on the left really isn't much of a neural network. It can do essentially linear regression. And the mathy way of saying it is it can solve problems where the inputs are linearly separable from the output. And you don't have to know what that means. It just means that this is really doing something pretty simple. It can't do very much at all. On the other hand, if we have a network that has one hidden layer, just one hidden layer, then it can approximate literally any continuous function, and it can compute directly any bounded computable function, given that that hidden layer has enough neurons. And so, here's a very, very wide network. You can imagine it has 100,000 neurons in this hidden layer. This can solve any problem. Now, the problem is, though, it was really hard to figure out what the weights were supposed to be for our neurons in our last example. It was really hard. And it turns out that figuring out what the weights should be for a really wide network like this, we would call this network wide, it's really, really difficult. it's, although this neural network could, in theory, learn any sort of computable function and approximate any continuous function, in practice, this neural network is going to perform much worse than this neural network, for example, which might have many less neurons, but is deeper. Another thing, though, is, throughout the last notebook, one of the things I think we all got an appreciation for is that it's not a super fun time to edit a whole bunch of weights in a neural network. Unfortunately, that's not how deep learning works. Instead, deep learning works by training the neural network. And so the way that this training sort of generally works is, well, first off, let's say we have an example problem. So let's say we are trying to train a neural network to recognize handwritten digits. We will be using the MNIST data set in this example. And so what we're going to have as the input for our neural network is going to be a picture. And this picture is going to be a 28 by 28 pixel image, and it's going to be black and white. So the dimensions of this input are 28 by 28 by 1. So if we want to feed this into a neural network, the way that we're sort of going to do this is the first thing we're going to do is flatten our input. So, here's our input of 2. We're going to flatten it. So here is our first layer of neurons. These are the input neurons. And if you remember back to that first example of the person looking at the flower, the first thing that happened is he didn't look at the entire flower. He looked at chunks, visual chunks. And here, each one of our visual chunks is a single pixel. Okay, so what we're going to do now is we're going to pass all of these pixels into our neural network, and then we are going to have several outputs. And here I'm making this a simplified MNIST problem. So instead of recognizing every possible handwritten digit, we are only going to recognize the digits 0, 1, and 2. And what we want is if the digit on the left, if our input is a 0, we want the top output to activate and the others to not activate. If it's a 1, we want the middle output to activate and the others not to activate. And if it's a 2, we want the last output to activate. So what we're going to do to train our neural network to recognize digits is we're going to just randomly initialize our neural network's weights. We're going to feed our image through the neural network, and we're going to get outputs. And if everything works perfectly, we'll get the correct activations. But of course, when we first initialize our neural network to random weights, we are not going to get the correct activations, and we'll just get sort of random activations. And so let's say we do this and we get the activations of 0.2 for digit 0, 0.6 for digit 1, and negative 0.3 for digit 3. This is completely the wrong answer. We don't even have the correct answer being positive. We don't have the correct output being positive at all. This is very, very wrong. What we're going to do to train the neural network is we are going to calculate how wrong the neural network is. So to do this, we're going to have a target in mind. So, we know that this digit should be a 2, which means the target outputs should be a -1, a -1, and then a +1. What we're going to do from here is we're going to measure how far off the mark we are. And to do that, we're just going to take a sum square error. So we take the sum square error, we get this value of 5.7. And then we're going to do something called gradient descent to figure out exactly how much each weight did wrong and what direction we should try to adjust that weight in. And I was drawing what to do, how gradient descent works at this point, and I realized that 3 blue, 1 brown did it better. So we're going to watch a small video that sort of explains gradient descent much better than I can.
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have 2 main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more to how this particular network performs and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of 2 hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. Then what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images. Fortunately for us, and what makes this such a common example to start with, is that the good people behind the MNIST database have put together a collection of tens of thousands of handwritten digit images, each one labeled with the numbers that they're supposed to be. And as provocative as it is to describe a machine as learning, once you actually see how it works, it feels a lot less like some crazy sci-fi premise, and a lot more like a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function. Remember, conceptually, we're thinking of each neuron as being connected to all of the neurons in the previous layer, and the weights in the weighted sum defining its activation are kind of like the strengths of those connections. And the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a 3, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer, that output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal. This average cost is our measure for how lousy the network is and how bad the computer should feel. And that's a complicated thing. Remember how the network itself was basically a function, one that takes in 784 numbers as inputs, the pixel values, and spits out 10 numbers as its output. And in a sense, it's parameterized by all these weights and biases. Well, the cost function is a layer of complexity on top of that. It takes as its input those 13,000 or so weights and biases, and it spits out a single number describing how bad those weights and biases are, and the way it's defined depends on the network's behavior over all the tens of thousands of pieces of training data. That's a lot to think about. But just telling the computer what a crappy job it's doing isn't very helpful. You want to tell it how to change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has one number as an input and one number as an output. How do you find an input that minimizes the value of this function? Calculus students will know that you can sometimes figure out that minimum explicitly, but that's not always feasible for really complicated functions. Certainly not in the 13,000 input version of this situation for our crazy complicated neural network cost function. A more flexible tactic is to start at any old input and figure out which direction you should step to make that output lower. Specifically, if you can figure out the slope of the function where you are, then shift to the left if that slope is positive, and shift the input to the right if that slope is negative. If you do this repeatedly, at each point checking the new slope and taking the appropriate step, you're going to approach some local minimum of the function. And the image you might have in mind here is a ball rolling down a hill. And notice, even for this really simplified single input function, there are many possible valleys that you might land in, depending on which random input you start at. And there's no guarantee that the local minimum you land in is going to be the smallest possible value of the cost function. That's going to carry over to our neural network case as well. And I also want you to notice how if you make your step sizes proportional to the slope, then when the slope is flattening out towards the minimum, your steps get smaller and smaller. And that kind of helps you from overshooting. Bumping up the complexity a bit, imagine instead a function with two inputs and one output. You might think of the input space as the xy plane, and the cost function as being graphed as a surface above it. Now, instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative of that gradient gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar with multivariable calculus and you want to learn more, check out some of the work that I did for Khan Academy on the topic. Honestly though, all that matters for you and me right now is that in principle there exists a way to compute this vector. This vector that tells you what the downhill direction is and how steep it is. You'll be okay if that's all you know and you're not rock solid on the details. Because if you can get that, the algorithm for minimizing the function is to compute this gradient direction, then take a small step downhill, and just repeat that over and over. It's the same basic idea for a function that has 13,000 inputs instead of 2 inputs. Imagine organizing all 13,000 weights and biases of our network into a giant column vector. The negative gradient of the cost function is just a vector. It's some direction inside this insanely huge input space that tells you which nudges to all of those numbers is going to cause the most rapid decrease to the cost function. And of course, with our specially designed cost function, changing the weights and biases to decrease it means making the output of the network on each piece of training data look less like a random array of 10 values and more like an actual decision that we want it to make. It's important to remember, this cost function involves an average over all of the training data. So if you minimize it, it means it's a better performance on all of those samples. The algorithm for computing this gradient efficiently, which is effectively the heart of how a neural network learns, is called backpropagation. And it's what I'm going to be talking about next video. There, I really want to take the time to walk through what exactly happens to each weight and each bias for a given piece of training data, trying to give an intuitive feel for what's happening beyond the pile of relevant calculus and formulas. Right here, right now, the main thing I want you to know, independent of implementation details, is that what we mean when we talk about a network learning is that it's just minimizing a cost function. And notice, one consequence of that is that it's important for this cost function to have a nice, smooth output so that we can find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. It's a way to converge towards some local minimum of a cost function, basically a valley in this graph. I'm still showing the picture of a function with two inputs, of course, because nudges in a 13,000 dimensional input space are a little hard to wrap your mind around, but there is actually a nice non-spatial way to think about this. Each component of the negative gradient tells us two things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitudes of all these components kind of tells you which changes matter more. You see, in our network, an adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to some other weight. Some of these connections just matter more for our training data. So a way that you can think about this gradient vector of our mind-warpingly massive cost function is that it encodes the relative importance of each weight and bias. That is, which of these changes is going to carry the most bang for your buck. This really is just another way of thinking about direction. To take a simpler example, if you have some function with two variables as an input, and you compute that its gradient at some particular point comes out as 3, 1, then on the one hand, you can interpret that as saying that when you're standing at that input, moving along this direction increases the function most quickly. That when you graph the function above the plane of input points, that vector is what's giving you the straight uphill direction. But another way to read that is to say that changes to this first variable have 3 times the importance as changes to the second variable. That at least in the neighborhood of the relevant input, nudging the x value carries a lot more bang for your buck. All right, let's zoom out and sum up where we are so far.
Okay. My only goal in life is to become as clear a communicator as 3 blue, 1 brown. I think that's impossible. Okay, so the big idea here is that we have this cost function, and it's a way that we can measure the performance of our neural network. And then we can use some calculus to actually figure out how to adjust the weights in our neural network to improve its ability at completing some task. And for us, the task that 3 blue, 1 brown was demonstrating was MNIST, the handwritten digit recognition task. Okay, so here's what we got so far. Right now, we have this neural network, and we have data that gets fed into the neural network. And, some of this data is inputs, it gets fed into the neural network. On the other end, we get our predictions. We also have targets that are in our data set, which tell us what we want our predictions to be. And we're going to combine them together into a loss function. And that tells us how our neural network is performing. And then we use gradient descent to actually optimize this loss function. And to optimize that, we make small adjustments to our weights. And overall, what we've learned today is that deep learning uses neural networks, and neural networks are just layers of neurons. And neurons compute this simple little function, this weighted sum plus a bias inside an activation. And the only thing we get to learn inside of this is our bias and our weights. And finally, we get to use gradient descent to optimize our neural network so that we don't actually have to hand design the weights of our neural network. Okay, are there any questions about what we've covered so far? Awesome, okay. So we're now ready to do actual deep learning. We are going to do the handwritten digit problem, we're going to do binding affinity, and I don't think we're going to have time for anything other than those 2 tasks, but those 2 tasks are more than enough. And the thing that's really fun about this is that you guys don't have to do any of the gradient descent code. You guys don't have to do any of the data loading and manipulation. You guys just get to play with neural networks and figure out how to make neural networks that work. And to do that, we're going to be using this framework. Yes? Oh, that's a very good idea. Okay, let's take a 5-minute break. Hey, I think we are ready. It looks like a lot of people had coffee. Very good decision. Okay, so this is the exciting part where we transition from sort of this theoretical stuff to actual practical stuff. And the way that we're going to do this is by using this framework called PyTorch. And PyTorch is, it does all sorts of stuff, and it's really deep, all the stuff that you can do with it. We are going to stay right on the surface. We are going to do nothing too complicated, but we're still going to do stuff that's cool. And so we're going to do a brief introduction into some of the stuff that we're going to be using with PyTorch, and then we are going to dive into some notebooks. Okay. So here is some Python code. Also, just for, I guess, just a quick survey, how many people here have used Python before today? Oh, wow. Okay. It looks like most of you have. For anyone that hasn't, that is completely okay. We'll be able to get through these examples, and you'll be able to sort of work with neural networks even without any Python experience. But so the idea here is Torch is PyTorch, and it's the library we're using for deep learning. So the top 3 lines are stuff that we need to actually be able to use PyTorch. And then the remaining lines are an actual usage of PyTorch. So here we're importing Torch. Here we are creating a neural network. This is a neural network that takes 1,000 inputs and has one single output. So the output is 1. It is a neural network with 1 neuron, but it expects 1,000 inputs. And we can make that with just this NN linear. And so if we were to look at it, this network would look like this. And we can test this neural network by creating some random input. And you aren't going to have to create any input. I'll handle with all the creation of inputs. You'll just be making neural networks today. And then we can actually print what happens when we pass our input through the neural network. So even though our input has 1,000 dimensions, when we pass it through our neural network, we get a single output, and that's because our neural network has only one output. And you'll notice that the output here is more than just the value. We see that it's this torch tensor type, and it also has this grad function right after the value. And that grad function is the thing that allows PyTorch to figure out the gradients of your neural network and actually do the optimization. We aren't going to do any of the gradient stuff ourselves today. If that is something that is interesting to you, then that is definitely something worth pursuing. But for today, I'll take care of all the gradients, and you guys will take care of all the networks. So let's look at another example. Let's try to create a network that is like this. So a network that has 1,000 inputs, then it goes to a layer of 256 neurons, to a layer of 512, to a layer of 128, and finally to an output layer of 10. If you were to do this by hand, it would be hard, but with PyTorch, it is easy. So there's a little bit more going on here, so we're going to go into it layer by layer, or line by line, excuse me. The first thing is we're using this NN sequential class. And so what NN sequential is it says, I'm a neural network, but I am a neural network made of a bunch of layers. And so give me a whole bunch of layers, and I'll glue them all together so that you can just pass your input through and you don't have to worry about what happens in between these layers. So this is really sort of a container class for more neural network layers. And inside here, we have a whole bunch of layers. So here is our first layer, which takes as input 1,000. So it takes in 1,000 inputs. And then it goes to 256 outputs. Our next layer takes in 256 inputs, outputs 512 outputs. Our next layer does 512 to 128. And our final layer does 128 to 3. And if we do the same sort of thing we did last time, it works. We create our input, we pass it through the network, and we see we get our values as expected. Now, we're missing one part of our neural network. NN linear has our bias and it has our weights, and it will take care of all the computation of doing that weighted sum plus the bias. But it does not do any activation function. And to prove that, I've multiplied this input by 100, and you can see our output is now greater than 1. So, no activation function is no good. And actually, you need the activation function not just to squash your inputs, but if you didn't have activation functions, then none of the neural network matters. This whole neural network is equivalent to a one-layer neural network that has 1,000 inputs and 1,000 inputs and 3 outputs. So you have to have your activation functions in here. And fortunately, they're easy to put in. All we need to do is pass in activation layers in between our neural layers. And so here are our activation functions. And whenever we put a new layer into our network, we just put in another activation function. And now when we pass this input through, even though it's a large input, we've multiplied it by 100, we still get something that is in the range of -1 to 1 because we have these tanh activation functions. Now, this whole time I've been using tanh activation functions, which is kind of nice because we have this range of -1 to 1 for our output. More common is sigmoid, which is a lot like tanh, except it has a squashing factor so that things are between 0 and 1. And our negative activations are just non-activations. Our negative examples are going to be activations of 0, and our positive activations are going to be 1. And when we pass this through, we can see we don't have any negative values coming out the other end of our neural network because the sigmoid is not allowing that. The sigmoid is squashing these outputs to be in the range of 0 to 1. And that is it. We are ready to do actual neural network stuff. So I am going to send another link in Teams, and then I'm going to do it along with you. Slack, excuse me. Only nerds use Teams. Okay, so inside the Slack lecture materials channel, we have the link to an MNIST collab page. And I'll wait just a minute for you all to load it up, and then we'll start working on it. And once you're here, feel free to connect just to get the VM allocated. Okay. So just like before, we have to run our setup cells, and I think we have 2 here, maybe 3. So this one loads, and yes, I want to run this anyways. This setup cell loads all the libraries we need. It loads PyTorch and Matplotlib, which we can use for visualization, and a couple of other stuff. This cell right here is going to load our data for us, and it's going to prepare our data. So let's see. Downloading. And it's also downloading MNIST for you, so it can take a couple seconds to run. There we go. Okay, we have one last setup cell, so we have 3 setup cells in total. This setup cell gives us some helper functions so that we can do all of our learning without actually having to do the backpropagation ourselves. And finally, this cell is an optional cell, but it just shows us what we're working with. So if we run this, it's going to show us some of our training data, and you can see it is indeed a bunch of handwritten digits. And this is exactly what we're going to be working with. Okay, so has everybody ran those cells? Okay, hands? Yeah, is anybody having trouble? Trouble hands. Okay, I'll just wait a second for people to catch up then. Okay. Okay, so let's move on to this training on the entire train set section. So there's some suggestions on how you can improve this cell, but let's just look at the cell first. Okay, so in the 3 blue, 1 brown video, he said that you train on the entire data set. You know, you take your loss function across the entire data set and then you backprop on that. In practice, that's not what you do. In practice, you train on a tiny subset of that data set called a batch. You backprop on that, and then you pick a new batch from your training set, and then you repeat that over and over again. So the batch size is labeled right here as batch size. If you have a small number here, you know, you're going to have a small number of images per batch. The larger this is, typically the better your network converges. But training can also be a little bit slower. Steps is how many steps we're going to allow our neural network to train for. So how many of these little batches, how many of our little gradient steps does our neural network get to take until we say, okay, that's enough, you're done. Learning rate is how fast it moves down the gradient. If the learning rate is high, then it's taking really big steps towards the gradient. And if it's really small, then it's taking really small steps. Usually small learning rates perform better, but they also take longer to learn. And finally, we have this loss function. And the loss function is just what we are using to compute our error. MSE loss is fine. You don't have to worry about adjusting this. If you want to, you can. MSE loss says we are taking the mean square error of our loss during our batch computation. Okay, and now comes the really fun part. This is our model. Now, you can't change the first line and you can't change the last line, and you also can't change the second line, but you can change everything else. You can add parts to the neural network. And so, for example, if I wanted to add a layer, I could copy this, paste it here, and I'd want to make sure that would work. And you have to make sure that the number of inputs and the number of outputs match up. So, you know, 3 here, that works out. 1 here, that works out. This neural network is terrible. You're going to have to work to figure out what the best number of neurons are, or the best width of your neural networks is, and also what the best depth of your neural network is. And that is it. We have that is completely correct. I need to add an activation function. Sorry, what was that? You know, you'll find that that's the answer for a lot of neural network decisions. Sigmoid is fun. You could put a TNH in there. And I think up here sorry, what's that? Up here I have a link that will give you a description of all of PyTorch's activation functions. Sigmoid and TNH works pretty well. Exactly. It's not a rule, that's right. Now, this does have one activation at the end that is a rule. And the reason that it's a rule here is because if we want to change our loss function, we need this specific activation function. It's not worth going into the details of that. If you want to look at that, the PyTorch documentation is there. But just for now, this is the only rule besides these 2 layers. Everything in the middle is things that you can change. And if you break anything, it's really easy to fix, so don't worry about it. And so what's going to happen is we create our neural network. This is the code that you're going to edit. And then this code tests our model, and it's going to test it on a training or a testing subset of the data that is not being trained on. And then we train our data, and then we get an ending test. So we get a starting test accuracy, and we get an ending test accuracy. And that is it. Okay, so if I run this, let's see if this runs. The play button is going. Okay, we have the starting accuracy of 8.9%, which is not great. And you can see the loss function is decreasing a little bit. This neural network is terrible, so I don't expect great results. Okay, we increased our accuracy from 8.9% to 43%. And here's an example of something we get wrong. This is a 5. We said it was a 1. And yeah, I think that we probably should have been able to figure out that was a 5, but the neural network is terrible. Okay, so that's it. Start trying to get a good neural network, and our only goal right now is to get the highest test accuracy we can. So yeah, just play around with it. If you have questions, raise your hand. I'll be walking around. Excuse me. And the last neural network layer, the output number has to be 10. So in this example, I can change the inputs if I wanted to, as long as I change these outputs. But this number right here has to be 10. And the reason it has to be 10 is because we have 10 digits that we are predicting. So if we make this any number other than 10, we're going to get an error because the dimensions of our tensors aren't going to line up. Just wondering, does anybody think they have the best accuracy here? Yes. 97.2? Okay. Yes. 97.5. 96. Okay, so still 97.5 is the number to beat, but it sounds like most of us are in the mid 90s, which is really good. If this was 20 years ago, you guys would all be first name authors on the biggest computer paper of the year. Okay, I think we're going to get diminishing results from continued work on this. So I'm going to let you guys finish for another 2 minutes, and then we're going to do one more thing in this notebook. Okay. So here's what I want you to do. Is everybody done running cells, or the cells done? Okay, cool. So I want you to grab your model, and I want you to copy it. Just this part right here. Okay, once we got that, we're going to scroll down to the next cell. And we are going to replace this with our model that we just made. Now, this is doing the exact same thing as before, except instead of training on the entire train set of MNIST, which is, let's see, instead of training on 60,000 images, we are going to be training on how many images? Let's see. Aha, instead of training on 60,000 images, we are going to be training on 500 images. And we're going to see how we can do. Okay, so now that we have our model inside this cell, this is the very last cell of the notebook, let's hit play and see what happens. The accuracy has gone down tremendously. And my guess is those of you who had the best performing models last time will have the worst performing models this time. So what's happened here is in the last example, we had way, way, way more inputs than our parameters in our model. Probably not way more, but we had a comparable amount. But now we have 500 training examples, and our model maybe has 1 million variables. Our model is going to learn every single image, and it's not going to learn what makes a digit. Instead, it's going to learn this image is a 1 instead of this digit is a 1. So try to fiddle around with your model and try to see if you can get a model that performs well on this very small train set. Okay, let's spend another 5 minutes and then we will move on to the next collab notebook. Okay, let's start to wrap things up here on this notebook. Did anybody beat 86%? Okay. 88.4, did anybody beat 88.4? Okay, that's the winner. I think there's a few more notebooks running, but 88.4 is hard to beat. Yeah, so what happened here is, we just had so much less training data that things became a lot more difficult. Modern optimizers and training for not a huge amount of time, but just enough, allows us to still get reasonable accuracy. What you would find with the previous example is if instead of training for 20,000 steps, you train for 2 million steps, if you're training on the whole data set, your model will get better. But if you were to do that on this, you'd find your model gets worse and worse and worse. And the longer you train, the worse your model gets. And all of this is things that you have to consider when you are working with sort of smaller data sets. Yes? I did not. And so one thing is that a solution our neural network could come up with is it could just memorize the pictures. And if it memorizes the pictures, it's learning something, but it's not learning what we want. It's not learning how to generalize. It's not learning digits. It's just learning pictures, which is maybe a much more boring thing to learn. So the way that we can test to see if our neural network is memorizing versus if our neural network is learning is by testing it on a different distribution of samples than we trained on. So what I've done is I've made 2 data sets. One data set is the pictures we use to train our neural network. And the other data set is a bunch of pictures that we're going to use to test our neural network on. And there's no overlap between the 2 data sets. And so although when we only have 500 images in our training set, we might be able to get 100% accuracy on our training set. As a matter of fact, we should all be able to get 100% accuracy on our training set. We will not be able to do that on our testing set. Our training set has too small a distribution to be able to do that. Okay. So the next thing we're going to do is binding affinity prediction. So let me link you all that notebook. Okay, and as we load up this notebook, there's one thing I want you all to do before you run anything. First off, is there anybody that hasn't opened the notebook yet? Okay, perfect. So what we're going to do is we're going to go to runtime, change runtime type, hardware accelerator, GPU. If that's not selected, you'll have to select it. Now, most of us are working on free accounts, so we aren't guaranteed a GPU, but most of us will probably still get a GPU. And if you can get a GPU, it will go a lot faster. Okay. If you really want to know, I think it's exclam SMI dash NVIDIA. Oh, thank you. NVIDIA dash SMI. And anyways. Okay, so I got a Tesla T4, which is not an amazing GPU, but is better than the one in my laptop. But I have a Mac, so. Okay, so once we're on our GPUs, we are going to download our data set. Now, hopefully this works. This is stored on my university box. So let's see. Moved permanently, that's not good. Okay. I'm going to turn off sharing for just a second while I try to debug that. In the meantime, feel free to look through the notebook while I try to figure out how to get us the data. Okay, so there is one thing I forgot. I made it so that if anybody was having a bot that went through GitHub and looked for links and code and just downloaded stuff, they wouldn't download and spam my box. If right here you see 2HM, please replace that with 2MH. And this will just make it so that you have the right link and are able to download everything. Okay. So the binding affinity problem is we have a ligand and it is docked inside a protein. And from that, we get a bunch of values that tell us things like the electrostatic interaction, repulsion, if there's any acid-base chemistry happening inside there, a bunch of things like that. And there's a few really, really big challenges for us. One is that this is something called tabular data. And what I mean by that is that none of the input fields have geometric relationships to any of the other input fields. You know, if I have a pixel in a picture and I have one pixel over, there's a clear geometric interpretation of what that means. And it turns out neural networks, even sort of dumb feed-forward neural networks, are really good at exploiting that sort of relationship. But when you have tabular data, it's really hard because there is no geometric relationship. It's just a bunch of numbers. And the numbers aren't very well related. And we know that because if you try to do a linear correlation on those numbers to binding affinity, it's terrible. So to figure out how to combine those numbers, the neural network has to do a whole lot. And it ends up being a really hard problem. The other thing that makes this really hard is that we don't have a whole lot of training data, or at least not a whole lot of high quality training data. The data set that we're going to be using for training is called DUDE, and the data set we're going to be using for testing is called LitPCBA. And the way that these data sets sort of work is they have about 100 proteins, and then a whole bunch of ligands, a whole bunch of molecules that bind to those proteins. And somebody's run the experiment and has said, okay, this ligand binds to this protein with this experimental affinity. They also have inside the data set a whole bunch of fake ligands that do not bind to the protein but look like they should. So we have done docking for both the real and the fake ligands, and we have a training set because of that. Now, the downside is that experimental data is pretty hard to work with. It's very noisy. The experimental conditions are not the same for everything, and there's loads and loads and loads of bias. And what I mean by bias here is, imagine if I gave you the problem that we did just in the last notebook. So imagine we were doing MNIST, handwritten digits, but I only gave you ones. Your neural network would have 100% accuracy, but it's not actually doing the problem. It's a really easy problem if you only have ones. There's too much bias in the data set. And the same way, there's lots of bias in our data sets. And to show that, we are going to test on LitPCBA, which is a different data set than what we're going to train on, which is going to be DUDE. So with that out of the way, make sure that you've run this cell, which downloads things and unzips things. Then we are going to run our setup cells. And finally, we can start doing some learning. So our input data has 17 fields, so it's a relatively small number of inputs for our model. And just like last time, put in more layers, make the layers deeper, change the activation functions, do whatever you want here, and let's see what you get. Oh, and one thing also. You will see that the accuracy is reported a little bit differently. So let me get this running, and I'll explain how accuracy works in this report. And it can take a little bit for it to start the first time because it has to warm up the GPU. Okay, so this first number is of all the ligands that should bind, how many of those do we find correctly? So we find 0.01% of the ligands that should bind. And so we are able to correctly predict a ligand should bind when it does 0.01% of the time, which is not great. On the other hand, we correctly say a ligand doesn't bind 99.949% of the time. So this second number is our true negative rate. So this is our true positive rate, this is our true negative rate, and this is our overall accuracy. This is what I think is going to happen. I think you're going to get okay numbers here, good numbers here, and terrible numbers here. If any one of these numbers is bad, the model is bad. If any one of these numbers is low, that's all that matters. If we have a low true positive rate, our model isn't good for anything. If we have a low true negative rate, our model isn't good for anything. We need to be generally good at both recognizing the positives and the negatives. And so with that, I'm going to let you start learning, and then in 5 minutes, 10 minutes, I'll come in with a small hint that will help us improve, and then I'll do that again in 10 minutes after that. Okay. What was that? It's somewhere around 10 to 1 in LitPCBA to 100 to 1 in DUDE. That is correct. And our actives are sort of more stringent, and so we say if it has a binding affinity less than or more than 30, or yeah, then it's excluded. So the threshold is very strict here, but it makes it easier to learn. That's right. The output is only one value. Does it bind or does it not bind? Okay, and just to clarify a misspeaking I had earlier, in this cell that we're doing, we are testing on dude as well as training on dude. And the next cell is when we are testing on lit PCBA, and you'll find that nobody does particularly well. For right now, though, who thinks they have the best accuracy? Yes. 70? Okay, yeah, that's pretty good. Anybody beating 70? Okay, so pretty much neck and neck. Okay, I'm going to do one more round around the room, and then I will give a hint. Okay. So I have actually cheated you all, and here's how. So if we look at the distribution of inputs, which we can do by running the very last cell in this notebook, what we'll see is every single input dimension, so every single, one of our input 17 values has a very weird distribution. All of them have terrible distributions. And the reason that this is sort of cheating you guys is because neural networks are notoriously bad at weird distributions of numbers. So here is the first thing we're going to do to improve our accuracy. We're going to go back to the top. Let's see, not quite the top. We're going to go to the second cell, so this cell right here. And we are going to put in, let's see, where is this? Let's see, actually, we're going to go to the very top of the cell, and we're just going to change clean equals true. Okay, so what this is going to end up doing is it is going to normalize our inputs, and it's also going to add in an extra layer of inputs. And this extra layer of inputs is going to record this field was 0. And if the field was 0, it's a 1, and if not, it's a 0. And the reason we do that is for a bunch of these fields, a 0 value means something special. It means for some reason this couldn't be computed, or this means something different than the normal distribution. So by adding this extra layer of input, we can greatly improve our model's performance. And also by normalizing the values, we can greatly improve our model's performance. So clean equals true. I'm going to run this cell again. And it takes a while to read all the data. And then it's done, and we can try training again. Oh, and one more thing. Once we do that, we have to change the first number of inputs from 17 to 34. I add in an extra, exactly, times 35. And 1 second, there is a bug somewhere. Oh, instead of 34, do 35. There is a throwaway value at the end. So clean equals true and 35 inputs for the first layer. And then things will train. Okay, Connor has an accuracy of 90% across the board. Is anybody beating that? No. Jeremiah, what, you got an accuracy above 90%? Yeah. Okay, Jeremiah has an accuracy of 94%, which is the number to beat. Now, we're going to ruin those accuracies though. If everybody would go down one cell before we were testing on dude, so we were testing on the same distribution of data that we were training on. If we run this, we will now test on a different distribution of data, and you'll find that you all do terrible. If anybody gets above 55% accuracy across the board, then I think that is state-of-the-art results on lit PCBA. Okay, so walking around, it looks like people are getting good accuracies on just dude, but nobody is getting good accuracies on lit PCBA. So here is the last trick we're going to cover today, and then we're going to work on this a little bit more, and then it is going to be dinner time. Okay, so the last trick, first off, I'm going to make a slightly beefier network. So I'm going to make this 500, 500, 1. So this is a wider network. It's not any deeper. So here is the trick we're going to do. We are going to add what's called a dropout layer. What dropout does, and it needs to be n.dropout. What dropout does is it will randomly, with, in this case, 50% probability, turn ones to zeros. It will randomly zero out your layer. And you might say, wait, that sounds terrible. And that's sort of the point. The point is that if your network is learning very specific things, if it's memorizing your data, it's not going to work with dropout. The only way your network will be able to learn if you are using dropout is if it actually learns something. So add in a dropout layer with somewhere between 10 and 50% dropout. And you can add multiple dropout layers if you want. And then let's see if anybody can get above 50% accuracy on lit PCBA. Okay, I think that's pretty much everything. So we didn't get around to predicting secondary structure, but we filled out the time, and I think there was a lot covered. I will give out the notebook for secondary structure prediction, and I don't know if it will make much sense without any sort of understanding of what's going on behind the scenes, but you can still play around with it. And with that, I guess that's it for now.